Hello dear student, myself Hrishikesh Labhade. I am working as an assistant professor at Srimati Vimlaben Khimji Tejokaya, S.V.K.T College, Devrali Camp, Nasik. I welcome you all in this online LMS lecture series. In today's lecture, we are going to learn about chemical energetics. This topic includes in Savitribai Phule Pune University's first year BSc Physical Chemistry Semester 1 course. Session agenda. In today's lecture, we are going to learn about enthalpy of neutralization, enthalpy of solution, integral heat of solution, differential heat of solution. We are also going to learn about heat of hydration, heat of fusion, heat of vaporization, and heat of sublimation. In today's lecture, we will also going to see the concept of bond energy, resonance energy, and an important topic which is Kirchhoff equation. This includes case 1, reaction when carried out at constant pressure, and case 2, when reaction is carried out at constant volume. At last, we are going to see the third law of thermodynamics, its application and its mathematical expression. At the end, we will see the numerical problems based on bond energy and resonance energy. Learning objective. In today's lecture, student will understand heat of solution, heat of sublimation, heat of vaporization, and heat of neutralization. In today's lecture, student will learn about bond energy and bond enthalpy of thermodynamics. Student will also learn resonance energy and third law of thermodynamics and the mathematical equation and application of third law of thermodynamics. From today's lecture, student will able to understand what is the variation of heat with the heat of reaction with temperature, that is what is Kirchhoff's equation under the constant pressure and constant volume condition. So, enthalpy of neutralization. The heat of neutralization of an acid by base is defined as the heat change when 1 gram equivalent of the acid is neutralized by 1 gram equivalent of the base when the reaction is being carried out in dilute aqueous solution. In similar manner, we can define the heat of neutralization of a base by an acid. For example, when 1 gram equivalent of hydrochloric acid is neutralized by NaOH or 1 gram of NaOH is neutralized by HCl in dilute aqueous solution, 57.1 kilojoule heat is produced. We can see the reaction there, NaOH plus HCl giving us a salt NaCl and a water. Generated heat is 57.1 kilojoule. Hence the heat of HCl with NaOH or NaOH with HCl is 57.1 kilojoule. Heat of neutralization of strong acid such as hydrochloric acid, H2SO4, HNO3 with a strong base such as NaOH, KOH or vice versa is always same, that is 57.1 kilojoule. This is because the strong acid or a strong base or the salts formed by them are completely ionized in a dilute aqueous solution. If the acid or a base, any one of them is weak, the heat of neutralization is usually less than 57.1 kilojoule. To understand this, let us consider a neutralization of weak acid such as acetic acid which ionize in a small extent with a strong base such as NaOH which completely ionizes. We can see the reaction 1, acetic acid giving us CH3COO minus ion and H plus, and NaOH ionizes as Na plus and OH minus ions. When H plus ion is given by acid, is combined with the OH minus ion given by the base. The equilibrium in the first reaction shifts to the right side, that is more and more acetic acid is dissociated. Then the part of the heat produced during the combination of H plus ions and OH minus ion is being used for the complete dissociation of acetic acid. Hence, the net heat evolved in the reaction is less than the 57.1 kilojoule. Next point is heat of solution. What is heat of solution? It is defined as a heat change, that is the amount of heat evolved or absorbed when 1 mole of substance is dissolved in large volume of solvent, that the further addition of the solvent does not produce any more heat change. There are two kinds of heat of solution. The first is integral enthalpy of solution and the second is differential enthalpy of solution. First, integral heat of solution. It is a heat change occurs when a specific quantity of solute is dissolved in a specified quantity of solvent under the condition of constant temperature and constant pressure. If the amount of solvent used is large, it's very much large, that the further addition of solvent no longer causes a change in the integral heat of solution, then the integral heat of the solution at that point is known as heat of solution at an infinite dilution. Second is differential heat of solution. Differential heat of solute at a specified concentration, specified temperature and pressure condition is the heat change observed per further mole of solute dissolved in such a large quantity of solution that no significant change in the concentration occurs. This is the definition of differential heat of solution. The next point is heat of hydration. It is the amount of heat change, that is heat absorbed or heat evolved when 1 mole of anhydrous salt combines with the required number of moles of water as to change into a hydrated salt. It is known as heat of hydration. Let us see the example of this. For example, copper sulfate, the heat of hydration is minus 78.2 kilojoule per mole. This is represented as the equation given below. Copper sulfate on hydration gives copper sulfate pentahydrate CuSO4 5H2O and delta H for this reaction is minus 78.2 kilojoule. Next is heat of fusion. It is the heat change that takes place when 1 mole of solid substance changes into liquid state at its melting point. For example, heat of fusion of ice having a melting point of 273 Kelvin is 6 kilojoule per mole and it is represented as follows. A water in form of ice when melts into water, the delta H fusion is 6 kilojoule per mole. Heat of vaporization. It is heat change that takes place when 1 mole of liquid changes into gaseous state at its boiling point. In this, the example is again water. Heat of vaporization, that is delta H vaporization of water into its gaseous state, that is water vapor, at its boiling point 373 Kelvin is 14.7 kilojoule. It is represented as follows. H2O, that is in the form of water, transferred into H2O vapor form, delta H vaporization is 40.7 kilojoule. Heat of sublimation. It is a heat change that takes place when 1 mole of solid changes directly into vapor phase at a given temperature below its melting point. Sublimation is a process in which solid on heating changes directly into its gaseous state below its melting point. Iodine, naphthalene generally show the sublimation process. The heat of sublimation, example is iodine. The heat of sublimation of iodine is 62.39 kilojoule per mole and it is represented as a equation given below. Now the next point is bond enthalpy or bond energy. The bond energy of a particular bond is defined as the average amount of energy released when 1 mole of bonds are formed from an isolated gaseous atom, or in a simple definition is the amount of energy required when 1 mole of bonds are broken so as to get a separate gaseous atoms. There are two cases arises for diatomic molecule and for polyatomic molecule. In case of diatomic molecules such as H2, HCl, etc., the bond energy is equal to its dissociation energy of the molecule. But in case of polyatomic molecule like methane, CH4, the bond dissociation energy, the 4 CH bonds are different, hence an average value is taken. Bond energy of some common bonds are given in the table below. Student should note that you shouldn't mug up this value, it's already given in the numerical. The heat of reaction can be calculated from above bond energy data. The following formula is used for that. Delta H reaction is equal to sum of bond energy of reactant minus sum of bond energy of product. Resonance energy from thermochemical data. Some molecules, as we know, get stabilized because of resonance going on in between the molecule. The extent of stabilization of a substance per mole of a consequences of the resonance is called as resonance energy or resonance stabilization energy. For example, benzene. Benzene has a 3 double bond which are at an alternate position, which shows a high stability, that it doesn't undergo the addition reaction under the ordinary condition. It prefers a substitution reaction instead, because to prevent its aromatic character. It is possible to calculate the resonance energy from heat of hydrogenation. We will see some example based on it. Heat of hydrogenation of cyclohexene, which contains only one double bond, is equals to minus 29 kilocalorie per mole. Heat of hydrogenation of 3 double bond in a 6-membered ring compound, so we will multiply minus 29 kilocalorie per mole into 3. We will get minus 87 kilocalorie per mole. So experimental value of heat of hydrogenation of benzene is minus 50 minus of 87. Thus finally we will get the resonance energy of a benzene equals to 37 kilocalorie per mole. Now we will see the variation of heat of reaction with temperature, which is given by the Kirchhoff equation. Heat evolved or absorbed in a reaction depends upon the temperature at which the reaction is carried out. The relationship showing the variation of heat of reaction with the temperature was first given by the Kirchhoffs in 1856. What is the Kirchhoff's law suggest? The change in the heat of reaction at a constant pressure for every degree of temperature is equals to change in the heat capacity at constant pressure at the reaction. Consider a general reaction as A reactant giving product as a B. Case 1. Reaction carried out at constant pressure. Suppose the heat of reaction, heat evolved at temperature T1 equals to delta H1 and at a temperature T2 equals to delta H2. Starting from point A at temperature T1, we can reach B at temperature T2 by two different routes, which are shown in the figure given below. Now route 1. In this case, we perform the reaction at temperature T1 to obtain B and at same temperature, and then heat this up to temperature T2. Then we will get heat evolved in the first stage as a delta H1 and heat absorbed in the second stage equals to CPB into in bracket T2 minus T1, where CPB is the average molar heat capacity of the product. So net heat evolved is equals to delta H1 minus CPB into T2 minus T1. Route 2. We first heat up the reactant to the temperature T2 and then perform the reaction to give a product at the same temperature. Then if Cpa is the average molar heat capacity of the reactant A, then heat absorbed in the first stage is equals to Cpa into in bracket T2 minus T1 bracket complete. Heat evolved in the second stage is delta H2. Then from above both equation we will calculate the net heat evolved is equals to delta H2 minus Cpa into T2 minus T1. As from root 1 and root 2 we get that the initial and final state in both the cases are same. Therefore, by law of conservation of energy we have net heat evolved by root 1 equals to net heat evolved by root 2. Now by comparing the equation, that is delta H1 minus Cpb into T2 minus T1 equals to delta H2 minus Cpa into T2 minus T1. By rearranging this equation and calculating delta Cp, we will get it as delta Cp equals to delta H1 plus delta H2 dividing T2 minus T1. Case 2. When the reaction is carried out at a constant volume, we have a known thermodynamic relation delta U plus P delta V equals to delta H. Under the condition of constant volume, that is delta V equals to 0. Now substituting delta V equals to 0 in the above thermodynamic relation, we will get delta U equals to delta H. Hence the above derived equation of case 1, we will replace it with a delta U and we will get the final equation as delta U1 plus delta U2 divided by T2 minus T1 equals to delta Cv, where delta U1 and delta U2 are the internal energy changes when the reaction is carried out at temperature T1 and T2 respectively. Third law of thermodynamics. This law was developed by German chemist Walter Nernst in year 1912. The third law of thermodynamics states that the entropy of perfect crystal at a temperature of 0 Kelvin, that is absolute 0, is equals to 0. The entropy is a randomness and it is denoted by a capital S. It is a measure of randomness in a system and directly related to the number of microstate accessible by the system. That is, the greater the number of microstate of the system, greater its entropy. At a temperature of 0 Kelvin, the following phenomena can be observed in the system. First, the system does not contain any heat. Second, all the atom and the molecule in the system are at their lowest energy point. A system at absolute 0 has only one accessible microstate, that is its ground state. Thus, as per the third law of thermodynamics, the entropy of such a system is exactly 0. We will see the mathematical explanation for third law. As per statistical mechanics, the entropy of a system can be expressed as S minus S0 equals to Kb ln of omega, where S is the entropy of a system, S0 is the initial entropy, Kb denotes the Boltzmann constant and omega denotes the total number of microstate of a system. As for a perfect crystal that has only one unique ground state, omega equals to 1. Therefore, by putting omega equals to 1 in above a statistical mechanic equation, we will get S minus S0 equals to Kb ln of 1, where total is 0, as ln of 1 is equals to 0. When the initial entropy of a system is selected as a 0, the following value of S, that is entropy, can be obtained as S minus 0 equals to 0, therefore S equals to 0. Thus the entropy of a perfect crystal at absolute 0 is 0. Now what is the application of third law of thermodynamics? An important application of third law of thermodynamics is that it helps in the calculation of absolute entropy of a substance at any temperature T. These determinations are based on the heat capacity measurement of a substance and given by the following equation. S equals to Cp ln of T or S equals to 2.303 Cp log of T. We will just replace the ln with the log into 2.303. Here the Cp is a heat capacity of a substance at a constant pressure, and this value is assumed to be constant in the range of 0 to T Kelvin. Now we will study some problems. The first one is, the student have to calculate the enthalpy change in the given reaction H2 gas plus Br2 gas giving 2 moles of HBr gas. We will also have the bond energy value of HH bond, Br bond and HBr bond as 435, 192 and 364 kilojoule per mole respectively. We can solve this problem by two methods. The first method is by calculating the total energy absorbed or released. Energy absorbed in the dissociation of 1 mole of HH bond is 435 kilojoule. Energy absorbed in the dissociation of 1 mole of Br bond, bromine bond is 192 kilojoule. Hence the total energy absorbed is equals to 435 plus 192, which is equals to 627 kilojoule. Energy released in the formation of 1 mole of HBr bonds is equals to 364 kilojoule. Therefore, the energy released in the formation of 2 moles of HBr bonds, which is equals to 2 into 364 as a 728 kilojoule. Hence the energy released is greater than the energy absorbed. Hence the net result of release in the energy is equals to 728 kilojoule minus 627 kilojoule. We will get the final answer as 101 kilojoule. Delta H equals to minus 101 kilojoule. Second method, using the formula directly. As we know, the delta H reaction is a summation of bond energy of reactant minus summation of bond energy of the products. Now we will substitute bond energy of hydrogen-hydrogen bond plus bond energy of bromine-bromine bond minus 2 into bond energy of hydrogen-bromine bond, which is equals to 435 plus 192 minus 2 into 364. We will get the final answer as minus 101 kilojoule. Second problem. Student have to calculate the heat of formation of hydrochloric acid at 348 Kelvin from the following data. We have given the reaction half hydrogen gas plus half chlorine gas giving HCl as a product, and delta H naught at 298 Kelvin is equals to minus 92,300 joule. The heat capacity at the temperature range is also given. For the hydrogen gas, Cp equals to 28.53 joule Kelvin inverse mole inverse. Chlorine gas, Cp equals to 32.26 joule Kelvin inverse mole inverse. Hydrochloric acid gas, Cp equals to 28.49 joule Kelvin inverse mole inverse. Solution to this problem. We have given the reaction. For this reaction, delta Cp equals to Cp of HCl minus half Cp of H2 minus half Cp of Cl2. We will substitute the given values in this equation and get the final as 1.91 joule Kelvin inverse mole inverse. It is given that the delta H1 is equals to minus 92,300 joule at temperature T1, which is equals to 298 Kelvin. So we have to find the delta H2. We will use the Kirchhoff's equation for this, which is Kirchhoff equation is delta H2 minus delta H1 divided by T2 minus T1 equals to delta Cp. As we know delta Cp, both temperature and delta H1, we can calculate delta H2. Delta H2 is equals to delta H1 plus delta Cp into T2 minus T1. We will substitute our given value of Cp and our finded value of Cp and all other values of temperature in the equation, which is equals to minus 9 to 300 plus in bracket minus 1.91 into 348 minus 298. The final answer is minus 92,395.5 joule. Assignment for the student. Questions. Student have to define the bond energy and how is the bond energy of a bond can be calculated for polyatomic molecule. and how it is used to calculate the enthalpy change of the reaction. The second question is state the third law of thermodynamics. Next question is what is the heat of vaporization? Fourth question is explain the heat of sublimation with an example. Student, in the next question have to explain in brief the Kirchhoff's law and derive its equation for the case when the reaction is carried out at the constant pressure. At the sixth question, student have to derive the equation for the Kirchhoff's law when the reaction is carried out at a constant volume. The last question of this assignment is student have to define the enthalpy of neutralization. Summary. In today's lecture, we study the heat of neutralization. Heat of neutralization is defined as the heat change when 1 gram equivalent of acid is neutralized by 1 gram equivalent of base when the reaction is carried out in a dilute aqueous solution. We also study the enthalpy of solution, which is defined as the heat change when 1 mole of substance is dissolved in large volume of solvent that the further addition of solvent doesn't produce any more heat change. There are two kinds of heat of solution. The first is integral enthalpy of solution and second is differential enthalpy of solution. We also see the concept of heat of hydration. Heat of hydration is a heat change when 1 mole of anhydrous salt combined with the required number of moles of water so as to change into hydrated salt as a product. Student, we also learn about heat of fusion. It is a heat change that takes place when 1 mole of solid substance changes into its liquid state at its melting point. Heat of vaporization. It is a heat change that takes place when 1 mole of liquid changes into gaseous state at its boiling point. We also learn about heat of sublimation. It is heat change, that is heat evolved or absorbed when 1 mole of solid changes directly into its vapor phase at a given temperature below its melting point. We also go through the concept of bond enthalpy or bond energy. It is the amount of energy required when 1 mole of bonds are broken to get a separated gaseous atoms. We also saw the important concept of Kirchhoff's law. The law states that the change in the heat of reaction at constant pressure for every degree of temperature is equals to the change in the heat capacity at constant pressure. In the Kirchhoff's equation, we studied two cases. The cases first is the reaction is carried out at constant pressure and we get the final equation as delta H1 plus delta H2 divided by T2 minus T1 equals to delta Cp. In case 2, when the reaction is carried out at a constant value, we get equation as delta U1 plus delta U2 divided by T2 minus T1 equals to delta Cp. Student, we also saw the third law of thermodynamics. This law is given by the German chemist Nurse in 1912 and stated as that the entropy of a perfect crystal at a temperature of 0 Kelvin is equals to 0. The entropy is a randomness of a system and it is usually represented by capital S. We also study the application of third law of thermodynamics, that it helps in the calculation of absolute entropy of a substance at any temperature T. The final equation for this application is S equals to Cp ln of T or S equals to 2.303 Cp log of T. Thank you.